Hi, my name is Christian, and I will give this presentation entitled Comprehending the Bending, a comparison of different test setups for measuring the out-of-plane flexural rigidity of a UD fabric. It's some work that I have been doing together with my co-authors Peter Broberg, Jørgen Kepler and Johnny Jacobsen. And throughout this presentation I will introduce different test setups for measuring the bending stiffness of a glass fiber fabric which we are using in our research. So for the motivation I want to show this example. It's a forming simulation onto a hemisphere mold which I have borrowed from Professor Boas and co-workers. And if only the tensile rigidity is included, we get a result like this, which is basically like kinematic draping simulation. If we add the shear rigidity, we can begin to capture wrinkles, for instance due to shear locking, but it's only when we include the bending rigidity that we get the full picture and we can capture the actual shape of the wrinkles. So we would like to have this bending rigidity characterized, and one approach is through experiments. So a bending test obviously needs to bend the fabric, but this gives rise to two questions, namely 1, what boundary conditions can achieve this, and 2, how do we extract the moment curvature relation, which is basically the bending stiffness. Luckily the literature can help us, and there are a number of tests described here. A very simple test is the Pierce test, and the idea is to cantilever the fabric until it meets an inclined plane, and then you can measure the overhang length and estimate the bending stiffness. The same setup also exists without the inclined plane, and we call that the free-hanging cantilever test. Then you can take a picture of the specimen and then use image analysis to extract the moment curvature relation. The same setup can also be done vertically, and this gives a little bit better control of the loading compared to just using gravity. We can also impose the rotation more directly using a rotational rheometer, and then we can record the moment. And lastly, we could also use a universal testing machine to compress the fabric and then study the buckling and post-buckling responses. So these are a lot of tests, and we want to answer the question which one is more applicable to the UD fabric that we are using. So the remaining part of this presentation will consist of 3 parts. First, I will give some more details of the test setups, and here I will focus on the buckling test because that's where we have introduced some novelty here. Then I will compare the test results, and lastly I will conclude with a discussion of the applicability of the different tests. So just to set the scene, this is the material that we are using. It's sometimes called a quasi-UD fabric because it has this stabilizing backing layer. It's quite thick, meaning that the bending stiffness in the 0-degree direction is quite high, and the bending stiffness in the 90-degree direction is not so high. And this is quite challenging, as you will see later. Okay, so let's dive into the details of the test methods. And first of all, there is a Pierce test, and as I said before, based on the plane angle and the overhang length, you can estimate a constant curvature independent bending stiffness using an analytical formula. Now the data processing in relation to the free-hanging and vertical cantilever test is a little bit more cumbersome. So first you have to acquire a digital image, then you can binarize it and apply filters, and then identify the center line. And once you have the center line, you can compute the curvature and the bending moment. But because of all these steps in the data processing, there are some user choices and therefore also some uncertainties in this test. But I can just mention that my colleague Peter is looking into those uncertainties. Alright, so for the rheometer bending test, you need this special fixture for the rotational rheometer. Now it can be shown that the arc length of the fabric is not preserved during rotation, and for that reason you need to allow for sliding in one clamp. And we achieve this using spacers. So during the test, the rotation is applied and the moment is measured. And then for the data processing, it is basically assumed that the curvature of the specimen is constant between the clamps. So there is an analytical formula that you can use, and it's a function of the rotation angle, but this assumption of constant curvature between the clamps as well as the sliding friction are the main uncertainties with this test setup. And then lastly we have the buckling test. So the idea is to install the sample in a universal testing machine and then compress it. And then you can measure the compression force. And after that there are two data processing approaches. The first one is to consider the fabric as an Euler column. It means you can look up in your favorite textbook on mechanics of materials and find this elementary buckling case, which relates the maximum critical load at buckling to the flexural rigidity and the length. The second approach is a little bit more involved, and that's an inverse model fit, and that's something we have developed for this test, which I will describe in the following. So this is a flowchart of how it works, this inverse model fit. And the first step is a bending stiffness model, which can output the bending stiffness as function of the curvature. Now we can feed this into our nonlinear buckling model, which can then predict the reaction force. And if we evaluate this model at multiple levels of compression, we can get a vector of reaction forces, which we can feed into our least squares optimizer. Now for that, we of course also need our experimental reaction forces, but then we can close the loop and we can let the least squares optimizer manipulate the bending stiffness of the model until there is a good agreement between the model and experimental reaction forces. Okay, so this is the overall idea. Now I'll go into some more details of these boxes here. So for the bending stiffness model, we are using an exponentially decaying function with 3 parameters, and that was chosen quite empirically. It consists of these parameters here, the maximum and minimum value, and then this parameter p, which controls the rate of decay. And this means that the bending stiffness will be a decreasing function of the curvature. And it also means that there will be 3 design variables in the least squares optimization, namely these two b's and the p. So for the nonlinear buckling model, we are using a Henke bar chain. So it consists of rigid segments connected by torsion springs. We can find the equilibrium configuration by minimizing the total potential energy, which is a function of the gravitational work and the bending energy. So basically we have chosen these torsional springs based on a beam in bending. Now the model here is connected to the left support and then just propagates out and is parameterized by these angles theta. And in order to make sure that it actually meets the right support, we have added these two constraints. But that is actually quite convenient because the force required to enforce these constraints is actually the reaction force. And that can be compared to the experimental cross-set force. So let's see how that looks. So this is the compressive force versus the compressive displacement. And as you can see, we can load up the specimen to around 17 newtons, after which it starts to lose stiffness. The blue circles are the least squares minimized model reaction forces that we have found. And the reason why we are only using the first part of the curve is that it had curvatures more than adequate to compare to the other tests, but in principle the entire curve could of course be used. Alright, so that was all the tests. Let's see some results now. And first I'm going to present results for the 0 degree direction. Here we see the moment per unit width versus the curvature and the results from the free hanging cantilever test and the vertical cantilever test. And you can see there is a decent agreement between the two, although the slopes are not quite the same everywhere. If we then add the rheometer bending test, you can see that at least in the beginning there is a decent agreement, but then they start to deviate, and here we have a discrepancy. If we then include the buckling test using the inverse modeling framework, you can see that, well, the agreement is not very good in the beginning, and at higher curvatures it's somewhere in between the previous tests. And then lastly we have the two constant curvature independent bending stiffness tests, namely the Pierce test and the buckling test. But as the other tests suggest that there is a strong nonlinear moment curvature relation, the applicability of these tests is probably questionable. So for the 90-degree direction, their results are not quite as good. The reason for that is that the fabric is very limp in this direction, and that's really challenging for the tests. The test that performs the most consistently is the rheometer bending test, but really, let's say that this is still a work in progress. So I'd rather spend some time talking about the 0-degree results again and the applicability. So as we concluded before, these three tests here, the free-hanging cantilever test, the vertical cantilever test, and the rheometer bending test, agree reasonably well at low curvatures. And this also makes sense because that's probably the region of highest fidelity. For the cantilever type tests, the high curvatures occur close to the fixation, and therefore these results could suffer from some boundary effects. On the other hand, the rheometer test suffers from this issue with the sliding friction in the clamp, which also increases at higher curvatures. Now, the buckling test from the inverse modeling framework, well, the agreement wasn't very good at low curvatures, and at higher curvatures it was somewhere in between. And actually the higher curvatures is where this test has its highest region of fidelity, because the low curvatures occur close to the buckling point. And let's face it, it's not a very good Euler column. So this maximum load here will be sensitive to imperfections in the fabric. So a conclusion based on this discussion could be to consider tests with different regions of fidelity when you characterize your fabric, so that you can cover the entire range of fidelities. Alright, so let's wrap up. In this presentation I have presented 5 different test setups for measuring the bending stiffness. There is the Pierce and free-hanging cantilever test, there is the vertical cantilever test, the rheometer bending test, and the buckling test. And I've tested this material in the 0 and 90-degree direction, and the response is quite different, as well as how easily it is to test at all. So overall you can say that the rheometer bending test performs the most consistently, also within the repetitions of the test, but it suffers from this issue of sliding friction in the clamp, as well as whether the curvature is in fact constant between the clamps. So the free-hanging cantilever test seems promising if these uncertainties in the data processing can be addressed. So what gray level threshold is going to be used, what is the curve fitting scheme, and are there any morphological filters, etc., etc. And lastly, there is the buckling test with the inverse modeling framework. It works for higher curvatures, or it could maybe also be used as a validation case, because the fabric will experience a wide range of curvatures from negative to positive and back again. So before we finish, I just want to advertise a little bit for our educational article about kinematic draping. And it also comes with a draping code in MATLAB of only 99 lines. And I think this can be a good starting point for more advanced implementations, but it's really intended for teaching. So please check it out, it's on GitHub. And lastly, thank you very much for your attention.